Hi, welcome to this video, which is a response to a code report video that I'm a little bit late to responding to, but there's just a couple of things I wanted to talk about. So first of all, I really love this video. Firstly, because I like APL, so any APL related stuff is cool to me. But secondly, the sort of message of the video is something that really resonates with me. The idea that the way in which APL allows you to relatively easily explore different approaches, sometimes wildly different approaches to the same problem, I find really fascinating and also really useful. However, I wouldn't be responding to this if I didn't have anything to say. So there are a couple of things. I want to basically show another sort of similar approach and talk about a couple of details in differences between an approach I thought of. I say I thought of, it's a pretty common APL pattern as well, and what Conor has done in this video. And I also want to talk a little bit more in some details that are relevant to do with the dialogue interpreter, because I know Conor uses dialogue APL, and for some things it's pretty fast, but there are some specific performance considerations that you might not know unless you're a little bit more familiar with the dialogue interpreter specifically. They're not really inherent to APL itself as a language, but they are worth considering if you are writing code in dialogue APL and performance is a concern of yours. But before that, the very first thing I wanted to kind of call out, unfortunately, is I think Connor's used the American President Lines shipping company logo instead of any actual APL logo. Now, I can understand the hesitation against using a dialogues logo specifically, because ideally you'd like to use a kind of vendor independent, vendor agnostic logo. And there's been a good number of attempts at that, or some logos that really were from a vendor but then kind of, got passed around as if they were just generic APL logos. But recently there have been a few concerted efforts, mainly on the APL Orchard, I think in some other places as well, to try and generate or create some kind of vendor agnostic APL logo. So if you are interested in graphic design or just seeing something come to life like this, then head on over to the APL wiki. There is a page now called APL logo with a couple of ideas. I know of a few other ideas that I'd like to see added here. One, I think if I can find the old chat logs for it, I thought was really cool. What was it? It was basically, I can just show it in the session. If you display the vector APL, then you get this kind of boxed output with a little arrow here. And I thought this is kind of, someone in the APL Orchard sort of took this idea and made a really cool stylized version of it. And I was thinking at that point, yeah, that is a good idea. It's really simple, so maybe it's a bit boring, kind of like this, but you can sort of take it and do whatever you want with it. Other than that, I'm allowed to give a personal opinion. I quite like this sort of cube one at the minute. But, I don't really have the strongest opinions. Anyway, so that's enough rambling about the logo. Let's talk about Connor's solutions. So, when I saw his video talking about this problem, so what's the problem? You basically have these possible sort of instructions on a really simple language. It's just an increment decrement language, bit of a Turing tape kind of deal. The first thing I thought was, well, if you're only incrementing and decrementing, then you are at the end of the day probably going to want some set of ones and minus ones that you can then sum, because because this does assume starting from 0, increment is 1, decrement is -1, you sum the whole thing, you end up with the final state, which is the problem statement. The kind of curse you have in the problem formulation on the page is that it asks you to process a kind of list of strings, and in APL that means a nested list of character vectors. And in most APL implementations, what that means is you have actually in here a length 3 array of pointers in memory, or pointers to places in memory, and the places in memory those pointers point to are the simple in this case length 3 character vectors, which are, you know, flat contiguous little blocks of memory that in this case say, you know, probably a Unicode code point for each of those characters. So the first thing I think in this case is, and I know Conor did something that was like a little train selecting those middle characters. I thought that was really excellent. But if you know a bit about nested arrays, you might know a couple of things like, okay, instead of making a little train like this, it might be more clear to use the bind operator, because the bind operator sort of tells us explicitly, okay, we're taking this function and we're filling one of the slots. We're taking a dyadic function that normally takes 2 arguments, and we're sort of permanently fixing one of the slots with a value, and that tells us that this function is always going to be called monadically. Whereas this version here can be called dyadically, but is essentially ignoring its left argument. So it's a subtle difference, but some people find that important. The second thing is that this is really the crux of fixing the issue from an APLer's perspective. You have this sort of nested array input, and what you really want to do is get out of that nested representation as soon as possible from a performance perspective. If you're just talking about representing a solution that's really elegant to look at, sometimes a nested array solution is just super neat and clean in terms of the notation. It could be just a few characters long. But if you're interested in performance, you want to get out of that nested regime and into flat arrays as soon as possible. And then once you've got the flat arrays, like this, it's just now a length 3 flat list of characters. Well, then you're laughing, really. You can do, you know, any number of different methods. So if we think about Conor's final solution there, which involved this kind of outer product with column-wise subtraction pattern, then that's one way of doing it. Another way that you might see, it's a bit more old school, is you just compare, you know, luckily with this problem, if we compare to one of the symbols, plus or minus, then we can fairly safely assume the other one will be the opposite symbol, especially when we're picking the middle element from these instructions. So it's a nice little hack in that sense, whereas I suppose technically this comparison's a little bit more robust. In case you get faulty input or something, it might catch that in a different way. But mapping from zeros and ones to ones and minus ones can be a matter of, what would we want here? I guess we might want to compare to minuses. I might flip this in a second, but the basic idea is to multiply by 2 and subtract 1. Yeah, this is what you want. In fact, this one, I want to flip these the other way around. There we go. So now you get the same result, but since you're just doing simple scalar arithmetic operations, I mean, technically you are here as well because you only have a matrix of 2 rows, but you're saving yourself an entire outer product comparison, which is not too bad when you've got a fixed input, but here we're doing half the comparisons in this version. but you get the same idea. And then you just simply do a sum, and that's your result. So I could call this one A, and I think there's one other really subtle point, and I'm not exactly sure what extent it matters. So I'll maybe take two versions. But if you the easiest way to convert from your expression to a function is to just slap an omega and surround it in curly braces. But when Dialog APL executes Dfns, it has to create an entire execution context for this Dfn, just in case you want to define temporary variables in there, or have guards, or any of the other mechanisms that Dfns allow you to use. In contrast, if we work out how to define this tacitly as a sort of train, and I'll show you double checking that this makes sense in a moment, then the function definition, I think, is tokenized at fixed time when I press enter now. That's in the interpreter as kind of not pure machine code, but a kind of more efficient to parse representation. It's not processing all of the, I think this is true, that it's not processing all of the symbols character by character every time, like it would be when executing a Dfn, creating that context and then parsing the actual code each time. Here, because it's defined as a point-free function, it sort of knows how everything is going to associate the moment it's fixed. I might be talking a little bit above what's the truth here, but I think that there's some element there where it's not much, and in practice it makes little to no difference in real application code, but for little programming puzzles like this with speed comparisons, sometimes doing a tacit version can be a slight improvement in terms of performance over a Dfn. So how do we tell that this is a correct tacit version of what we're talking about? Well, I have a link in the description to my webinar about trains and how to read them and how to write them. But basically you're looking for patterns of 3 and then 4, and then odd, even functions and arrays, which is a pattern that you can learn without too much effort. So basically you have to recognize what a function is. So I know this from just experience. And then you just count the functions and arrays and make sure it's the right number that makes sense. So right tac refers to our right argument. Then we've got pick each, so that's 2 things, which are 2 functions. Then we have an array. So this is an array function fork, so that's 3. And then plus, literal plus glyph equals, that makes another fork, where the right time is itself a fork, and then times 2 makes another fork, and then -1 plus makes another fork, and then finally we have a plus slash makes it a top overall. So I've rattled through that. I'm not going to go into details, like I said. Link in the description for a webinar about how to parse trains. And then finally, there's a couple of other things I want to add before I do a runtime comparison. One is, I was actually pretty inspired by the tally minus the count of minuses. That seems like a great idea to me because, but it's plus and the sum, 2 times the sum. Yeah, okay, we'll figure that out in a second. Because the tally is super efficient in APL because it just has to look up some bit of information in memory at the beginning of an array's definition, includes its shape, and so tally can just figure out how many elements, or it's just the first element of the shape really. And then a sum. Now sums of 1s and -1s is integer sums, and I think there could be some like vector instruction magic going on under the hood that makes that nice and fast for large arrays, but I know that Boolean processing in APL can be even faster. So once again we want to get out of the flat regime, we want to find the minuses, sum that up 2 times, and it's the count minus 2 times the sum. Is there a nice way to write 2 times the sum? I think we might just need to parenthesize that to make it a fork, the right tie in itself another fork. So that's another way of expressing what Conor called his first solution. So tally is now counting the tally of a... In fact, we get even more efficient representations because we're coming out of the nested regime here, pull out the second element of each and make that just a flat array. Then we're doing a simple comparison, and so that becomes a Boolean vector, which is even more efficiently represented in APL, because APLs usually have bit Booleans. So that's squeezed right down in memory usage, and they can use special SIMD within a register type dealies to process those fast. And then, count of an array is pretty efficient. A sum on a Boolean list is pretty efficient, or can be made very efficient in some circumstances. Multiply that by 2, etc. So then we're going to call this C, and we're going to check the same sort of scheme. So it's function, array, and then another function atop that. So that's an atop overall. To me, B and C, for me personally, are really pushing the limit of what I would call an acceptable, for me personally, tacit expression or tacit definition of a function. You get any longer than this, and I'm really going to be asking you to make it a Dfn and or something like that. But that's just me personally. Not everyone feels that way. And finally, I guess let's put Conor's final solution up, just to be a bit mean. So I don't remember it exactly, so I'm gonna have to toy around a little bit. Actually, it's at the bottom of this image, isn't it? So you have to use a membership because he's comparing 2 characters to flat arrays. So using membership to get the flat Boolean result here. Plus minus jot.member, and then do the rest. All right, plus minus jot.member right tack. Then it's a minus reduce first. That becomes an entire part, and then finish it off with a plus slash to make an atop, where the right tine of the atop is itself an atop, but it's quite a long atop, so we'll call that D. So Conor likes using CMPX. I like the runtime user command. Runtime user command is literally just a thin wrapper over CMPX. Does the same job. It's just I don't have to copy anything first. And I'm also going to do a couple. So we've got X, which is kind of the example Conor was using. But if we look up here, back to where I had this definition, we can also make something called Y. And Y is going to be this array indexed by 10,000 instructions randomly selected. So X is going to be our little short one, and then Y is 10,000 instructions, so we can get a comparison in a different space. 3 instructions is not a lot, so the interpretive overhead is going to be sort of the main difference. Whereas with a large input, now we're starting to see APL's array processing kick in. So A of X and A of B of X, B of X and C of X and D of X. Maybe I should have saved my comments about array processing for this time when we're waiting for expressions to run, but you live and learn. I can't remember what these look like. Oh yeah, and then we've got this issue as well. Is there any other way to show these that's a bit nicer? I don't know. Usually I quite like, let's see how small we can get away with. This will have to do. So we'll look at the comparisons and then we'll look at the definitions. So you look at B, you can see a 10% difference even though it's an identical algorithm, and that I guess has got to be chalked up to just the Dfn. C seems to improve a little bit just because you're doing a sum on a Boolean list and then a tally minus, and that's just generally a bit less processing maybe. I'm not sure. It's really much of a muchness. You can see they're all in the order of microseconds here for this input, and the last one being a bit slower. Well, we'll see to what extent that really is a difference when we compare with Y. So this one will take a little bit longer to run, but the only thing I want to say about Conor's final solution, which here is called D, is that whereas the his previous solutions doing the 2 squad each, so 2 index each, whereas here I'm using a 2 pick each, it's the same sort of idea though, pulls the data out from the nested representation into a flat representation before doing the main processing. Conor's final solution D here actually makes the membership function do all of that nested array traversal. So this membership function, in doing its comparisons, it's having to do 2 comparisons where all of my solutions are only doing 1. It's comparing plus and minus, whereas I'm only comparing plus, or I'm comparing minus. And secondly, it's having to traverse the giant nested list, so that's 10,000 pointers it's having to chase and then get the data out of different parts of memory. Whereas if you pull out into a flat representation first, then you're doing this equality on flat contiguous chunks of memory. And I think in some parts of Dialog APL and other APLs, you're basically processing at memory throughput speed almost, because equality is such a basic operation. Well, I suppose with Unicode code points, maybe there's some other stuff, and I'm not an APL implementer, so you must take everything I say in this video with a grain of salt, but I think the general ideas that I'm talking about are largely true. So yeah, getting a tiny little speed up maybe by doing the tally minus 2 times the sum of a Boolean list, but apparently there's not much in it. So to finish off, there's our 4 solutions, the Dfn and 3 trains. And as I kind of said, you know, this is kind of true of many APL, especially modern APL implementations as they stand today, is that the most quote-unquote elegant solution in terms of maybe fewest characters or kind of looking neat might not necessarily be the most performant in terms of memory and CPU processing use. And that's just what happens sometimes. So that's all I wanted to say. I think this video has become longer than I initially anticipated, so if you're still here watching at the end, thank you very much. And I'll see you the next time I decide to do something like this. Bye for now.